The first problem is burst balloons. There are n balloons numbered from left to right. Every one has some value, and when you burst a balloon, you get some number of coins. That is the number written on the left balloon times this one times right neighbor. Here left and right are adjacent indices of I. After the burst, the left and right then become adjacent. So the I disappears, and the next two, they are glued to each other. Find the maximum total coins you can collect by bursting the balloons optimally. And we should assume that balloon minus 1 and n, those outside the array, have value 1. Here's an example. If you're given array 3, 1, 5, 8, it's apparently optimal to first remove 1. For that you get 3 times 1 times 5, which is 15. Then remove 5, you get 3 times 5 times 8. Then remove 3, and the left neighbor is treated as 1, and so on. There is some array. And after I burst a balloon, it disappears. Say that numbers are 2, 3, 7, 5, 10. Then it disappears. The remaining ones are 2, 3, 5, 10. And because the limit in the problem is small, like n up to 100 or maybe 500, we should first think about dynamic programming maybe. And for that, it's a bit, we shouldn't just go from left to right, for example, because we might pop balloons in some very strange order, like on the right, on the left, on the left, on the right. Going from left to right isn't a good idea. Then maybe we should use dp of LR. That might be reasonable. But after popping balloon number 7, what we should read, what dp we should read, it might make sense to iterate over balloon I to pop, and then to say that we merge the left part up to I minus 1 and the right part from I plus 1. But it isn't a good idea, because after that, when you pop this one, the value of 3 will be used. So it matters. We can't just take this dp of I plus 1 to R to just read this value, because it depends on what is there on the left. Because of that, we need to do something else. And from time to time, we should consider analyzing the process backwards. And it will work here. Instead of thinking which balloon I should pop first, I will think which balloon I should pop last. So when I have that, say 2, 3, 7, 5, 10, I will say, okay, maybe I'm going to pop this one last. For that I will get score 1 times 3 times 1, because I imagine that there is 1 and 1 at the ends of array. And because this is my last move, so all of that was apparently removed before that. Before that, this 3 is non-removable, because I say this is the last one, the last balloon to pop. And I can just read dp from this interval, because this interval knows what is on the left. It's this 3 that cannot be destroyed before the interval 7, 5, 10. When we imagine the process backwards and we iterate over the last balloon to pop, it makes sense to take, so that when we iterate over this balloon I, the last one to pop, I will say that the score is A of I, where A is, let's say, that array from the input, times A of, here, this is L, this is R, times A of L minus 1, times A of R plus 1. This is the score we get from popping this balloon, plus before that, we have dp of L I minus 1 plus dp of I plus 1 r. And this is dp of some interval, like this one, is the best score we can get here, assuming that number on the left, the next number on the left, and the next number on the right, they will not be destroyed before this whole interval is destroyed. And I'm going to just code that in LeetCode, in C++. This is two-dimensional array. Let me create n to make code a bit shorter. This is array of size n times n. Now, in some order, I will iterate over elements. I'm not yet sure if this is a correct order. I will think about it at the end. And here I will return dp of 0 n minus 1. For the last, I iterate over the last balloon to pop. dp of lr is maximum of itself, and I prefer to name this array, say a, it will be shorter. A of I times a of l minus 1 times a of r plus 1 plus dp of l I minus 1 plus dp of I plus 1 r. There are some small issues with that, like this might not exist. This might not exist, it can be outside the array. Similar for this one, maybe I minus 1 is smaller than L. And then it's some extra thing to write. L, then 0, and then that, otherwise 0. R is n minus 1. If yes, then 0, otherwise that. And here L is smaller equal I minus 1. If yes, then this, otherwise 0. And I plus 1 smaller equal R, that, otherwise 0. I don't want to put 0 here, instead it's 1. Things outside the array are 1. I miss some bracket. Here we go. And I didn't close something else. Output 63, expected 167. It's not correct. Test case. Let's try it for just a single 5. Oh, I said that I need to fix this order. So dp of lr uses values dp for smaller intervals. Like for example from L to I minus 1 here. So we want all those shorter intervals to be already computed. Because of that, here I will iterate with L decreasingly, so that when L is 0, already values for L1, 2, and so on are computed. Then let's change it back to the sample input, run code. And it's correct now. I will submit. The complexity is of n cubic. Runtime error. Okay, the input can be empty. Then this is not the correct thing to say. No elements exist. I need to say if a empty, return 0. can we say the largest element of array will remain at the end so that we get that and then we remove backwards? Why would that be optimal? Why should we leave the maximum element to the end? I don't think it will be optimal. As I said multiple times, don't care about those things. Coding challenges aren't about squeezing your solution to be just a bit faster than others. There are some constraints, some time limit decided to check your complexity, and that's it. I don't recommend here trying to make it faster than, say, 99% of people. It's a waste of time. I like rolling dices. You have d dice. Each die has f faces numbered 1, 2, up to f. Return the number of possible ways, modulo that, to roll the dice so the sum of the face up numbers equals target. Well, this is problem 1155. This is just, should I post something like that in the chat? I guess so. This is just like an knapsack problem, where what is important after some rolls is what is the sum so far, not really the values, and this will be the dimension of my DP. And I can code that very quickly. I don't think it's too interesting. So, because after rolling, say 3 times, and if we get 2, 5, and 4, so the sum is 11, it's the same thing for us as if we roll 3, 3, and 5, and then we get sum 11. We care just about the number of those. Because of that, dp of s will be the number of ways, and here the number of ways because they ask us for the number of ways to get some s so far. I could create here another dimension for the number of rolls. I can start with this dp, but anyway, I do it roll by roll, so I only need the previous row of this two-dimensional matrix, so I will just create one. dp, I will call it ways of target plus 1, ways of 0 is 1. Initially there is one empty way to create sum 0. Wait to get sum 0. For repeat how many times? D times. New ways. There will be new array that I will create, and then ways, I overwrite ways. At the end I return the number of ways to just get target. This size is enough to store sums from 0 to target. I don't care about bigger ones. Sums, what are the constraints? 30, 30, 1000. I think that should be enough. We'll see after implementing loops, we will see what is the complexity. For sum already from 0 to target. For every outcome now, so now pipes, I think, is the name of the new number that appears on a die. Pipes smaller equal f, there are f faces. If already plus pipes smaller equal target, I don't care about bigger sums, then ways of, no, new ways already plus pipes plus equal ways of already. This could be done with just one array if we iterate in a good way, but this is easier. There is Modular, right? Yeah. So I will create modulo, and here we should do, I will create a helper variable, not to repeat code. tmp plus equal that, if tmp is greater equal mod, tmp minus equal mod. I could use modulo operator, but this is faster. Modulo operator is slow. So I more often do this if. The complexity should be what? O of D times target times F, which is good enough for the constraints, but it's possible to solve it faster, so maybe I will do that in a moment. Accepted. The thing is, if you have some array and you move to another array, no, this number will be the sum of those. Let's say that F, the number of faces, is 3. Then if the sum, this is sum 0, 1, 2, 3, 5, 4, 5, and so on, then this number will be the sum of those underlined places. This is how my algorithm works. And then to compute this sum quickly, I can use prefix sums. So I could say prefix of target plus 1 from, or I could just use prefix on the array ways. Target. And here it will be ways of I plus equal ways of I minus 1, and here modulo. I will create a function for that. At A plus equal B if A greater equal mod, A minus equal mod. This adds the second number to the first one. So add ways of I minus 1. This computes prefix sums. Then for new sum from 0 up to target, new ways of new sum is, it's the sum, it should be the sum from new sum minus F to new sum minus 1, which is ways of new sum minus 1 minus ways of new sum minus F minus 1. This sum is the same as this difference on prefix sums. Then I can remove that. And again, we need to care about going outside the array. I will change that to 1 because the 0th element will be 0 anyway. And here new sum minus F minus 1 greater equal 0. If yes, then that, otherwise 0. It's not the prettiest code, but it does the job. Submit. And now the complexity should be, integer overflow, because I need a subtraction. Here I will say if new ways of new sum is smaller than 0, new ways of new sum plus equal mod. Similarly to addition, this is how you can avoid modulo operator. Accepted. Now it's faster than 99% of people, but again, the complexity matters and you should understand your complexity. Do you think that hard LeetCode questions are challenging enough for someone at your level? I'm really curious to hear that. Some coding interview problems are hard because they're very different than competitive programming problems. I need to think about those. They are not standard. Similarly, in my when I was in university, there was some algorithms subject that was generally easy for me, but some exam questions were very hard because just I'm used to do a lot of competitive programming and all the techniques there I know. But if the problem just requires some thinking and it's not about just applying prefix sums and FFT, then I'm not that good in that. And sometimes I need a lot of time to figure out a solution, especially with caring about like constant space complexity, stuff like that is very, very unusual in competitive programming. Maximum Subarray sum with 1 deletion. I guess the title says what the problem is about. return the maximum sum for a non-empty subarray with at most one element deletion. Without deletion, it's called, there is cadence algorithm for that. Normally we go from left to right, and it's kind of a DP that at every moment we know what is the maximum possible sum so far, and also maximum found already subarray. Then we try to continue that. And now possibly in that thing that we already started, we have one element that is erased already. As I always say, what is important so far after we make some decisions? When we are, say, here, either we have a subarray that we continue, or we have a subarray that we continue, but already one element is deleted, or maybe something was taken on the left and it's a possible answer. Then I will store that in variable best possible answer so far. So this thing will be this will be suf no deletion, and also there will be suffix that already has a deletion, and I need to move between those states. Again, it will help me to create n, makes code shorter. Answer is the subarray needs to be non-empty after deleting one element. If it could be empty, I would say that answer is 0. Now I will say that answer is array of 0, I guess. Length is at least 1. In particular, I can take the first element. Normally I would here put some minus infinity, but it's safer to not think about infinity and just use that. Then suffix no deletion is array of 0, suffix deletion is 0, I guess. And then we move from the first number. We could also here move from the 0th number, but I would need to initialize those two differently. And then what? New. If I already deleted something, then I can say that self-deletion is max of. If element was already deleted in some suffix, I can expand it by 1. So suffix deletion is changed to suffix deletion plus a of I, and that is also saved like suffix with already one element deleted. Actually, I will write this as suffix deletion is max of deletion already plus a of I, or suffix without deletion and without any number. So this means, this thing means remove the ith element. Then suffix no delete is max of suffix no delete plus a of I, or just maybe a of I itself. Answer is max of answer, suf delete, suf no delete. Do I have to remove? With at most one element deleted. So it's okay to say that element was deleted or not. Return answer. You can always change the name of the argument. Does it work? It does. We could also solve a problem with k possible elements deleted. Then it's like, right now we had something like int dp of n2. Just I didn't store the whole array, I just remembered last two elements, where dp of n0 means 0 elements were deleted, dp of n1 meant one element is deleted. We could also make this thing, then complexity will be O of nk. So k is given in the input, and we say at most k elements can be deleted. And that was problem maximum subarray sum with one element deletion. Can you explain the DP states once? Will be very helpful. I can repeat that. Not getting the logic, can you repeat? Okay, let's try that. Some elements were already considered. They were some on the left. And let's say we are right now here. This is I. Maybe I points to this number, maybe this number. I just think about a vertical line. Maybe we want to continue a segment that we already started. So a segment like that. We don't care what exactly numbers were there. So we don't care if maybe, we don't care about the length of this segment. We don't care about what numbers are there exactly. We care about the sum. So if there are numbers 7, 2 and -3, I know that possible sum of such already started segment is 7 plus 2 minus 3, which is 6. And I take maximum of those. This would be up to this position, suffix with best sum, biggest sum. And I will consider continuing this thing. If there is 2 here, then for this new I, the best suffix will be 6 plus 2. But what is possible is that I have some suffix where I removed one element already. And among those possibilities, I want the best one to maybe continue it in the future. I don't care where this element that is removed is, what is its position. I just want to find the best suffix up to position I with one element already removed. The best means the one with maximum sum of non-removed elements. So the drawing shows a possibility of suffix with one element removed and sum 9. Maybe there is something better. Maybe this, say, green one, this one will give us a better sum, or either without element removed or with element removed. Then this is the value I store. And if I have those values computed optimally, I want to move to the same thing for the next I. After considering this one new number that could be negative, then I need to consider that maybe a moment ago I had suffix that is without removed element, but here there is something very small, or not that small, but considering something doesn't hurt. So then up to this position, this is a possible suffix, like with one removed number, I can just take 6. Without removed number, I can take 5. And this is what my transitions here do. They consider, oh, not this code, this one. They consider here from suffix with already deleted element. If I extend it by AI, I get again suffix with one deleted element, or I take suffix without removing everything, and then I remove AI. This is why here I don't add it to the sum, because it's removed. Given two integer arrays, return the minimum number of operations, possibly 0, needed to make array 1 strictly increasing. It's a cool problem. In one operation you can choose 2 indices and do the assignment. If there is no way to make array 1 strictly increasing, return -1. Okay, we have array 1, 5, 3, 6, 7 that we want to make increasing. Now, there is also second array, 4, 3, 1. What we can do is we can take any element from the first array and we can replace it with something from the second array. Like we can replace this 6 with a 4, because 4 is here. Our goal is to make the first array strictly increasing. There can be no ties. The goal is to make the first array strictly increasing, and it might be impossible. There was some example in the statement given where the answer was -1, what meant not possible. What is here optimal? Replace 5 with 3, change this into 3, change this into 4. Then we have array 1, 3, 4, 6, 7, and it's strictly increasing. If we care about increasing array, it might be good to just go from left to right. And then after we already modified in some way a prefix, if we have some prefix already, 153. We modified it in some way. What is important so far? The usual question that works for almost any DP problem. Because we minimize the number of changes, it's important how many changes we made, and also what is the value, the new value of the last element. Because this is something that we need to compare with the next element that we'll consider in a moment. It doesn't matter if 5 was changed to something small or not. It doesn't matter whether this 1 was changed at all. It's matter what is the new value of 3. For example, if the new value is 4, then we know the next number should be at least 5. From this, I get the idea that it should be dp of position I and new value, say v, like value. The value can either be what was there a moment ago or something from the new array, like something from that second array that is given, because we can replace values with something from that second array. We leave it as it is. Time limit exceeded. Oh, I forget about the part when I should care about complexity now. I do that during code forces contests. Here I focus on explaining. My complexity is size of A times size of B times size of B. It's very easy with DP usually, because you just see what for loops you have. It's actually harder with recursive DP, because then it's not that trivial. And when constraints are up to 2000, I can only have quadratic complexity, not cubic one. So I need to get rid of one of the for loops. And here, if the second array is big, let's say it has numbers, instead of 4, 3, 1, it has numbers 5, 10, 15, 20, 25, 28. And the previous number was 15. It doesn't make any sense to change the next number to 25 or 28. Also, it doesn't make any sense to change into one of those. So I will here say if v0 is different than b size, maybe I will create a vector of important indices to check. Time limit exceeded still. I didn't expect that. Maybe I wasn't right about this thing with complexity. Here it took 50 milliseconds, and this is what I would expect. Here it took almost 1 second. Okay, I think they don't use auto optimization flag. And if that's the case, maybe I should avoid this vector of indices. I can do that. Let me try some hacks. Creating a small new vector is slow. Maybe just because it wasn't optimized, it was bad. Okay, now it's sped up to 50 milliseconds. Maybe that was the reason. Creating a lot of small vectors. But I'm used to doing everything with auto optimization flag, then it doesn't matter. The complexity was good. That is important. -01 flag. Thanks, Alex. Okay, so maybe that's the reason. In ID1, the same thing worked 10 times faster. and I would get accepted first time. We could add here binary search at one moment. So instead of doing this part linearly, I could add binary search, but it doesn't affect the complexity. We do it only once every n repetitions. The statement is quite long. Follow-up. Sometimes follow-ups are interesting. Indeed, maybe it doesn't make a lot of sense to wait for a long time. What about this? So, is it true? Maybe that's enough. Max of 0 and I minus 5. Unless there are repetitions. I will remove repetitions, a resize, a begin, a end, minus a begin. So if two adjacent elements are equal, then I remove them. And then my claim is, my guess, is that maybe we shouldn't wait for a long time to take a new element. Instead of iterating from 0, I just iterate over last 5 elements. Maybe even last 3 elements will be enough. No, not enough. Then I'm worried that just tests are weak. For last 4 elements were enough. Oh, let's try to prove it. Or find a counterexample. What will be a nice counter test against my solution that I tested here, where I just consider going from last k elements after removing repetitions, adjacent repetitions. I wonder what should be, how the test should look like to make this thing fail. Maybe the numbers should increase for a long time. Like, yeah, maybe that's the test, the counter test, to create something like 1, 2, 1, 2, 1, 3, 2, 3, 4, 5, 6, 7, 8, and then 7, or something longer, of course. Oh, you don't see it. Nine, 10, and so on, 100, and then after that 99. I think the optimal solution should take 1, 2, 1, 2, 1, then 100, then 99. And it needs to make a jump like that. And LeetCode doesn't have such a test. That's an issue with problems that... I guess that's an issue with platform that has thousands of problems. Not all of them will be well prepared. Codeforce's problems also from time to time don't have strong tests. And my solution passed on LeetCode. It got accepted, but it is not correct. I understood that only thanks to here checking it myself. You can contribute a test case. Contribute. Here we go. Because your tests are weak, my solution passes, even though it's wrong. Is it that incorrect solution? Oh, it's not this problem. Because my wrong solution passes your tests. Will I get points because of that? This is pending. Contribute a test case plus 100. Redeem. What will I get? By the way, contributing a question, if that includes preparation, it is a lot of work. I should add 60 more tests and I have a t-shirt. I don't think that's nice money per hour. It's still something. I will later see what were the average numbers on Twitch and YouTube. Right now we have, oh, that's quite nice. We have 12 on Twitch. I guess because it's LeetCode and thanks to that there are some viewers. My boring, if I put boring programming stream in a name, it isn't that good. I don't know what is right now on YouTube. $38. The question, if you don't know, is whether I should keep streaming on Twitch or just stick to YouTube. And okay, that's it for today. How long? See frequently asked questions in the description. I didn't compete on LeetCode so far because it's the middle of the night for me. It's the wrong time zone. Okay, that's it for today. Like the video, subscribe to the channel, and yeah, see you next time. Bye bye.